Hey people, we are back.
Hello.
What day is today, Opa?
Today is Thursday.
Thursday is the 11th of February. It's a very big day.
Mm-hmm.
Not just because it's reunion day, because of Chinese New Year, but it is the International Day of
Women and girls in science.
Women and Girls in Science. It is. So we celebrate the diversity in having women in science.
Yeah.
And 2 days ago, on the 9th of February, we just celebrated on this panel here on the IUPAC Global Women's Breakfast.
Mm-hmm.
You spoke.
Yeah, I spoke.
You spoke with a number of people, different age, different background here,
Yeah.
and you represent a high schooler and one of the few male participants alongside yours truly.
Yes.
So it's important to also have the male to participate in the conversation to engender more diversity, in STEM, particularly in gender, right? To bring more females in this field as well here. Yeah, so we celebrate today, okay?
All right.
2 occasions. One is this day.
Mm-hmm.
The other day is
Your Chinese New Year?
Lunar New Year. Do you celebrate as a Korean?
I mean, that is a Korean New Year. I think it's tomorrow.
Same for us. It's tomorrow. Today is the eve, right?
Yeah.
Okay. We can catch up later.
All right.
Okay, so our final question for the day, right? So let's try to end on time, right? The people are already waiting to eat with the family, right? But you can eat as you listen up. Okay, go.
So the following reaction doesn't work.
Oh.
So we need to explain why it doesn't work, and we need to suggest an alternative method that could work.
Okay. Well, Opa, when I see this kind of question here, the interpretation I have is it will give you some other products.
Mm-hmm.
That means if you put these reagents and these chemicals here, it will give you something else.
Mm-hmm.
So in order to do well, right, we should not look at what's given here like, oh, it doesn't work. Because if you have this so-called wrong answer in your mind, then you are like confused.
Yeah, then you end up there.
You end up there, and when you end up there, you're wrong. So the way to do this is right. Okay, just ignore this and say, okay, these are the chemical we have. What you get, and then just do, and then okay, you have the answer here, and then you compare with this, and it's the same. Then that's really bad for you.
You skip the question.
Okay, but what I'm saying, you can really get it right, lah.
Yeah.
Cool. So let's do that. Okay, Opa, cover this. I'm blocking.
Mm-hmm.
Can we go through what are the functional group on the left?
So we have an alkyne over here, and then we have the COMe, which is an ester.
Ester. So it's like a symmetric ester, but this molecule is not chiral. It's not chiral.
Yeah.
So what is mainly?
So mealy is an organolithium. So I think we treat it as the same as a Grignard reagent.
Yes, and this reminds me of the question just now, right? When we have the bully. Bully, mainly these are very common chemicals of organolithium.
I see.
And because it's similar, I see a carbanion ion, CH3 dot negative, right?
Yeah.
It is a nucleophile.
Ah.
And the nucleophile will attack the electrophilic site of the substrate.
Yep.
Which would be the carbon.
Mm-hmm.
Right. 2 equivalence means?
2 equivalent means that we put 2 moles of this for every 1 mole of this.
Very good. So the ratio is 2:1.
Yep.
So if you have $1, I have
2.
If you have $3, I have
6.
If I have $100, I have
200.
If I have $500, we have
250.
Exactly. So you see the ratio thing is the ratio between this and that is always 1:2. Very good. Let's go.
All right. So we have this, and then
Alkyne.
yeah. So we put the mealy.
Mm-hmm.
So let's have one molecule.
One. Okay, one at a time. Okay, good. Go.
So we have 1 molecule of mealy.
You just go in. And it will eject
the OMe.
OMe, right, methoxide, and then replaces it with a methyl group to form a ketone.
Yeah.
Okay, good. Then next.
So we have 2 equivalent, right? So we have 1 more.
Then.
And then where will it go? So I think it goes over there.
Okay, so this is the question, right? That you prefer to go to the ketone rather than the ester, which you wanted.
Yeah.
Go. So what's that so?
So I think it's because ketones. Ketone is more this carbon on the ketone compared to that carbon on the ester, right?
Yeah.
So I think this carbon on the ketone is more electrophilic.
More electrophilic which means that this carbon here prefer to receive electron rather than that. But isn't it counterintuitive because the ester has an oxygen.
Yeah.
Isn't that electronegative and electron withdrawing?
Yeah, so that is the, I think that is the inductive effect, right? But then you also need to consider the resonance.
Did we show you that later on, or we should use the board to sketch it out for them?
We should use the board.
Okay, let's use the board now. Xingnan.
Alright, so let's use the board.
And where's my marker?
Here.
Okay, thank you. Okay, let's erase the previous drawing. Thank you very much. Thank you very much. So we have Sensei versus Oppa. Okay. Good, good. Okay, good. Actually, we changed because okay, I'm Sensei. Okay. Yes, what we're talking about here.
So we're talking about the ester versus ketone, right?
Very good. So let me just draw the ketone with the esters, right?
Okay.
Yeah. So we put the delta plus on the carbon, delta minus on the oxygen, right?
Yeah, and it's the same here.
Yeah. So if you have a single mode of nucleophile, you would prefer to go here than there, as evidence, right? So why is this selectivity? This chemoselectivity. Why is that so? Show us a bit more.
So, well, first we can draw the resonance for this one. Right, so this electron goes here,
Very
this
good.
goes here.
Very good.
Then we get O plus with a minus.
So what it means is that for the ester group here, because the existence of the real lone pair of electrons on this oxygen, it can really give to the carbon that's a bit more electron deficient, right? It feels it. This is called the resonance effect. Okay? But for this side, there's no resonance because next to this carbonyl carbon, there isn't any lone pair around to push.
Yep.
Right. So merely we have inductive effect. Okay? And inductive effect in general is a bit weaker, but there are exceptions.
Yep.
The exception comes in when you have a CF bond. This is a very strong inductive effect because fluorine is the most electronegative element.
Yeah.
So in this case, if you just compare right in this manner, the carbon here, just put a star.
Star.
Yeah. So the carbon star, right, compare this carbon without a star, that carbon receive electrons, kind of injection. Now here I don't have. So if you ask me, nucleophile attack the site that wants more electrons. This is no-brainer.
Yeah.
So to elaborate a little bit more here, the resonance effect, the lone pair is like, I'm a rich man. Oppa is a
not so rich man.
not a rich man, right? Then I'm the oxygen here, but you know, I have the lone pair, which is like so-called money, not in the form of this, right? It's like, okay, come, if you need it, I can
thank you.
yeah, share with you here. Then you can feel richer. This is real resonance, okay? But then I say, hey, that's mine. Pass it back.
Okay.
Then you can return in this form here. You see? At least he feels it. You know, he can take it, right? Yeah, for a while and return. But in inductive effect is when I'm the rich person, rich in electrons again, rich in experience, but I'm a stingy person. Which means I hold it like, hey, oh, you need something? Then okay, here you go. No, you hold it, you can, yeah, you can take it. But you see, I don't let go. You see, I don't let go. I don't let go because it's mine. You see, that's how it is. That's how I see energy. Okay? That's inductive. Resonance is real. Okay? So let's come back to it.
Alright, so let's have the screen down once more.
Screen down. Oppa, can you pass me a bottle?
Your bottle?
Sure, come. Okay, what color is this?
Well, it's orange.
It's orange. It's so festive, right? Luminary.
Okay.
Orange. Go.
Yeah. So this is why it doesn't work.
Because at the so-called second equivalent, it will
go to the ketone instead of the other ester.
Exactly. When you have a grignard, or in this case your butyl lithium, it will form a tertiary alcohol. Too bad.
Yep.
So that's why it fails. So if you're able to show us this way, you have answered the first part of this question here, why it fails, because it have a side reaction, or the real reaction that occurs. So the next part of this question is to
propose an alternative that will work.
Let's do this.
Right, so actually I thought of two alternatives.
Okay.
Yep. So let's go over them one by one.
Okay.
So I think the first one.
Yep.
So the first one I said is to protect one side of the molecule.
Okay.
So
It's the same side, other side works, right?
yeah.
Okay.
So what we can do is so let's say we have the ketone over here. Then we protect it.
Okay.
Then the melee has no choice but to go over there.
Very good. How do we protect a carbonyl group like a ketone?
I mean, there's many ways to protect the ketone. So I think one way is you can use ethylene glycol.
Oh, can you draw it out something? Because it's all name. Do we have it here in the slides?
No, we don't.
Okay. But maybe you have something else later on?
No, I don't.
Okay.
Yeah.
So that means it's only one solution, not the S lah.
Oh no, there's one solution over here.
Okay.
But there's nothing for number one.
Okay. So audience, right? Remember there are two solutions. We'll hold it because you see both, and then we talk about it one by one by drawing out, right? Okay. Good. Drawing out the structures of the ethylene glycol.
Yep.
Yeah. Okay. So we're gonna have acetal protection, or in a higher level, in level 3, that's called dition reaction. I'll talk about later. Okay, go.
So
protect, yeah.
I think I'll have to draw on the board, right?
Oh, what about the second one?
We're talking about the second one.
Yeah.
So the second one is we can convert esters to acid halides.
So that means at this stage, right, you will
go over here because acid halides are more reactive.
Ah, right. So you see the two approaches, right? There's the thinking that you can acquire. One is if you do nothing, this is going to happen. This means that this happens, which is undesired because this guy is more reactive to this
guy.
So his approach is just in life, right? What you do is you do a decoy. If this is reactive, you make sure this is not even available. You block it. You block it by protecting it, right? So that's not even the target. That's the only target is here. Whack, and then you go. Okay. The other way is this is reactive. Now you make the other side more reactive. More reactive. So you make it into something that want to receive more lone pair of electrons from nucleophile. And recall, what are the highest pedigree for this carbonyl group, right? CO double bond here is the acid chloride. Acid anhydride is a bit below, but acid chloride is the best. Ivan, you want to challenge it? Acid chloride is the best, right?
Yeah, it's the best.
Okay.
But I kind of don't like this solution because if we use acid halides, right, it causes environmental something.
Okay,
because
so
it releases HCl or something.
Good. So Ivan, your crew here talked about he doesn't like it in the lab. We try not to use it because when we use it, the side product, it is a condensation reaction. You form HCl gas, and this is pretty against the principle of the green chemistry. So you form something negative, like okay, sure, you go green, don't do it. But just for the sake of theory, it works. Okay. So shall we focus on this side first to show the class how do we protect the carbonyl group?
Alright, so let's have the slides up.
Slides up, please. Slides up, please.
Slides up.
Okay. You want to dust that as well?
Oh.
Okay. So we're saying that we should protect the ketone, right?
Yeah.
Oh, that's a simple ketone, acetone. The first member in the ketone series. What do you put there?
So my first instinct is to use ethylene glycol.
Okay, let's try it out.
Or it's known as. Yep.
Very good. Okay, ethylene glycol, ethylene. I will write it for you. Why is it ethylene?
Well, because there's two carbons, right?
Two carbons right here, two carbons, like ethylene, like the main skeleton here, then glycol, you have two diols here on the wings left. Okay? You need a catalyst for this reaction.
Right, so it's an acid catalyst.
Very good. So, of course, to prove it from mechanism. Okay. So, I will start, okay? People remember, H plus goes red. Please don't proclaim this. It's here. So, height. Okay?
Okay.
And then you form the O plus. Come, O plus, continue.
Okay, so now well, the ethylene glycol has to come in. Any attacks? This goes up, and then
you can turn a bit. You don't see. Yeah.
H.
Very good. Yeah. So of course we know the final product here, right?
Yeah.
The product is like this, right, Opa?
Mm-hmm.
So for me, when I see this, right, I'm seeing this ketone here. Like when you put this and two alcohol, it will form some funny looking alien. That's how I see it. Yeah, so you don't have to use Italian glycol. Basically, I can just give you something like this, right? Opa, that's how I do it. For me, I just do 1, 2, 3, 4, 5, and I don't know even what is it here, right? Because in the end, I just condense it and form something like that. That's how I see.
Oh.
1, 2, 3, 4, and I like this hairstyle more. But you get the point here. Yeah. That's it, right? But so of course, you just need a catalyst. Okay? Good work. So how do we come to here?
So, well, first thing is you have to get rid of this, right?
Very good. Remember, people, we want this to link and come here, right? To join this carbon, we want this to go. To make it go, that's why with the H plus, take it and then form H2O, and then eject as water. Right. And then the OH from the ethylene glycol come in to replace it, and voila.
OH.
And this is protected, which means that if I have the ester here, right? Some ester, you have the presence of methyl, you can't attack because it's no longer carbonyl group, no longer electrophilic, only position. Cool? Ivan, anything on chat? Singlan?
No.
Okay. Okay. So how do we protect it?
So, well, we use acid catalyst again.
Exactly, just use acid catalyst. So we add some more H plus, and then you go back to
a ketone.
Can we draw that over there?
All right.
Okay. Another way of protection in higher chemistry is called the dithion. But if you use this right in CM121, you overkill. You overkill, but you're such a wow, you're very zai, you're like, wow, what is this, right? Okay. But actually, it's nothing very fancy, right? Even dithion, you know about it, is the sulfur, right? It's just like that.
Yeah, oh. You need in this type of reaction, you need to take care that you only use the dithion for ketone, don't use for aldehyde.
Exactly. Why is that so?
Because if you use two aldehyde, right, it will make the hydrogen.
Yeah.
So let's say this one is hydrogen.
Yeah.
It will make this hydrogen slightly acidic.
Correct.
Then milli will attack it.
Alright. Okay. So Ivan and I are talking a little bit more difficult topics here, but I'm saying that you see that I like chemistry because you can dope. Not say taking drugs, but doping means that you do a direct substitution of the elements in the same group. So oxygen, sulfur, they're from group 6 called the chalcogens.
Oh, okay.
Oxygen is the first element, sulfur is the second element there. We normally regard O's, right? Simple. But the sulfur can just take their place and do the same thing, and there's still protection.
Oh, okay.
But anyhow, just for now, right, to just whack the appetite, you hear from me called dithion, but ignore it. Just I'm just showing off for a while because we are coming to the year of the ox, right? It's auspicious. Yeah. Okay, cool. Do we need to propose a second reaction?
A second reaction?
No, there's solution too. We should. Okay, last bit. Yes. Just a bit more here. Remember your second proposal was to convert the ester to something more reactive than ketone, right? That is the acid chloride. So, please, come. Now, I wish I can keep the hairstyle, but I'm going back to Call of Duty again a couple of weeks time. Okay.
All right. So, well, we have. So I'll just draw one ester. CO2. Okay, I'll just draw it up.
Yep. Thank you. So what you wanted to do is
not very clean.
Yep.
How do you do this? Two arrows means it's like more than one step. Go. Come.
So the first, I think what I'll do first, I'll just make it into a COOH. So carboxylic acid.
So from ester, the ester, you want to convert into the acid, right?
Yep.
What's the process called?
Well, it's called.
It's a hydrolysis, right?
Oh yes, it's a hydrolysis.
Cut this one, right? So you can use just H plus, H2O, and just heat, right? The hydrolysis. Next step, that's what.
So next step, we just have to replace the OH with the Cl.
Yeah.
So I think there's a number of reagents that can do this.
Okay, let's try.
So I know SOCl2 can do this.
Yeah.
I think there's phosphorus also.
Okay, or
I think there's PCl5.
PCl5, or
PCl3.
Yeah.
Cannot PCl3.
PCl3?
PCl3 cannot. Okay.
Oh, is it?
Why is it so, Ivan?
Why is it so?
I don't know, but never heard that reaction.
Okay, actually PCl3 works, but it works best for alcohol, less for the acid. It's about mechanism. So PCl5 exists as I recall it exists as a more liquid solid. This is more liquid gas. So you try to use something that's a bit more stable for the reaction here. Okay, but most of the time we like to use SOCl2 because the byproduct in this reaction is sulfur dioxide. So it is entropy driven. The byproduct for this is you have your phosphorus oxide somewhere. Okay, and if this is in the same state as a substance here, we need to do like a column chromatography to filter it. It's a bit harder. So we think more practical, like if the side product flies away, what remains are very key.
I see.
Okay, so you just do a two-step conversion to form acid chloride, and when you to a ketone, this will attack.
Yep.
That carbon, because you have a better leaving group called the chloride. Okay?
Yep.
Are we good?
We're good.
Very good. Okay.
Yeah, that was what I said was not really environmentally friendly, right?
Yeah, not very environmentally friendly. Okay.
Yeah.
So we have the screen down again before we end.
All right. Let's have the screen and the slides.
Right. So that will just how's the light? It's good, right? So to conclude, we have done tutorial 3. First time ever on Twitch without any audience here, just the 4 of us here. We can have reunion right now. Lunar New Year celebration. Come, the crew please join here. So I would like to thank people who are just tuning in. Again, there's no money, Ivan, please. Good things come in a pair, right? In a pair as well.
Thank you.
Like what else comes in a pair? What else comes in a pair?
No money inside.
No money. I told you no money. Don't check no money. It's already good things come in a pair like enantiomers and diastereomer. What else?
What?
The oranges, but we don't have it today. We have it next week here.
Yeah.
So allow me to wish everybody, come closer, a very happy Lunar New Year. Wish you family a prosperous, healthy, and a happy year ahead.
Well, I'll say it in Korean. So 새해 복 많이 받으세요. 설날 복 많이 받으세요.
Selamat merayakan tahun baru Tionghoa.
祝大家2021牛年扭转乾坤，牛气冲天，牛年大吉 ，Happy New Year！
Wow, that's great. I only know 年年有余。年年有余。Then over to you.
No， 扭转乾坤牛年大吉，牛气冲天 ，Happy New Year！
Yeah, that's very good in Chinese. So thank you. I'll see you soon. Okay, bye.